And our next speaker is Lucien from Uppsala, where he's a PhD student and he's giving his first talk on a conference, and he asked me to ask you to be kind.
Okay, welcome all. My name is Lucien and I'm a PhD student in Uppsala. And today I will talk to you about QresFEP 2, accurate, fast and reliable hybrid topology FEP for protein mutations. So I'll start by talking a little bit about the past, about our single topology approach, which was called QresFEP, which was published in 2019. And then I'll move on to our new dual/hybrid topology approach. And we have tested this with different topologies and restraints. And we tried to comprise a generalized protocol, and we tested the performance and compared it to other methodologies. And finally, I want to touch on some prospects that we still plan to do this for this project, which is jumping on the machine learning train. And we want to train a model to predict the error in our predictions, basically. So more on that later on. So first, QresFEP, single topology. It was an automated protocol for free energy calculations on protein mutations in Q, published in 2019. And Q is, it was already mentioned before by Jens Carlsen, is our open source MD engine developed in Uppsala, and it's specifically designed for simulations of biomolecular systems. So QresFEP works with a successive annihilation of the sidechain atoms of the wild-type residue to alanine. So I've shown here an example for which would be the largest transformation, the tryptophan residue, which is then stepwise with the electrostatics and van der Waals parameters annihilated by the charge groups to end up with just an alanine sidechain. So in this case, it would happen in 9 consecutive FEP transformations, which would then construct of your typical lambda windows. And if we do this both in the protein and in the reference tripeptide state, you will be able to predict the thermal stability or shift due to a single point mutation, which was already pointed out by previous presentations, that this is important to calculate, and it's also important for understanding protein-protein and protein-ligand binding. But in this case, we would only be able to do this to an alanine. So if we would construct the conformation of a mutant residue, you can combine these two thermodynamic cycles to basically determine the thermal shift for any residue to another one. So this was benchmarked on the T4 lysozyme set, and here I've shown the results, which compared very well to FEP+. But we do it in a shorter amount of time, because this I will point to the boundary conditions. So on the one hand, we have a dielectric continuum, which is an approximation and therefore quite quick. But on the other hand, we have the more expensive infinite periodic conditions, where you would have your large system in a box with multiple copies. And this is your traditional computational cost versus complexity or level of detail trade-off. And these, with Q, we work with finite aperiodic boundary conditions, which would end up somewhere in the middle. So how does this work? These are usually spherical, also in our case, and they are fast and they don't use artificial symmetry. And to mimic the bulk conditions, we apply the SCAS, so the surface constraint all-atom surface, which uses an attractive half-harmonic potential and a repulsive Morse-like potential to mimic these bulk properties of water on the edge of the sphere. And your MD will end up with a classical unrestrained part and then this restrained part. So now to our QresFEP 2, so the dual hybrid topology approach. I will first show some results. So we again did the benchmarking on the T4 lysozyme set. This is a well-studied system and widely used in benchmarking. Shown here are in magenta where the mutation sites are in this protein. And the new protocol compares very well again to both our single topology approach and FEP+ approach, which is great because it is even quicker than our single topology approach. I'll come back to this later. The only downside from this set is that it's only 43 mutations to alanine. And with the alanine mutant conformations, you will run into fewer problems since it's just a methyl group, so you don't run into problems with which conformer would your mutant actually have. So therefore, we also tested this on the ribonuclease Barnase set, another well-studied benchmarking system. And here we have 109 mutations where 20% start from alanine or glycine and 45% go to alanine or glycine, so at least half of the set is to non-alanine. And here we've compared it with PMX, and yeah, we show again very comparable results, which we're very pleased to see. And again, because of our finite periodic boundary conditions, we can run this in a faster time. So now I will touch a bit upon the method. So what I exactly mean with this dual/hybrid topology, because these terms can sometimes be used interchangeably. So on the one hand, we would have a dual topology, which would be two individual sets of atoms for, in this case, the wild-type isoleucine residue in green and the mutant threonine residue in magenta. And on the other hand, we would have a, in this case, maximum hybrid topology, where we use the same set of atoms for the atoms that are mutually the same in both residues, and we only start diverging the topology in the atoms that differ. So in this case, it would be only the oxygen for the threonine, and then in the same position an ethyl group for the isoleucine. And then would be another hybrid topology, yeah, in principle. But here we use a larger dual part. So here the backbone atoms are the same for both residues, and only we start diverging the topology from the side chain point. So this is the strategy in the end that we chose. So this what I would call the most dual-like hybrid topology in a sense. And the benefit of this is that it's much easier to automate, and also that you are not touching any bonded parameters, since the backbone of the residues will always be the same, and just the side chains are differing, that you turn on and off, basically. Another point that we investigated was applying distance restraints to hopefully benefit the sampling efficiency. So here I've overlapped a potential mutant conformation for the threonine on the isoleucine, and here you see that you would have 3 heavy atoms that overlap, on which you could apply distance restraints. But it might well be that your mutant conformation ends up something like this. So then you would have to, you can use fewer restraints, and the question is then which restraints should you use, or which restraints are best to use. This was also shown yesterday, I think, in the cartograph talk, that this can actually make quite a difference. So here I have a clip of a random isoleucine to leucine mutation, where you see the leucine atoms, which are now fully dummy, so they don't experience the surroundings. And you see that the orange atoms are flapping around quite a lot. And in the next lambda window, they would be turned on, which can then be turned on in a very erroneous conformation, which is not actually the mutant conformation that you should be looking for, which we encountered leads to both crashes, as well as between separate replicates, large errors. So we try to investigate this into a more systematic manner. Here is taken as our example the Barnase tyrosine 24-phenylalanine mutation. And we tested this with the maximum hybrid topology, so which is now shown in the clip, where we would just change the hydroxyl of the tyrosine into hydrogen for the phenylalanine. And we also tested this with the dual topology approach, where we use different sets of restraints. So now we move on to this slide. There's a lot of stuff happening, but I'll talk you through it. So in the top left corner, we only apply C-beta restraints, so only on this atom right here. And you can see now that the orange phenylalanine ring can translate quite a lot and spin around even, in the dummy state, which is the thing that we want not to be happening. Then in the top right corner, now we also apply restraints on the C-gamma, so the first carbon of the ring. And you can see that the translation from left to right is already much less, but the ring is still allowed to flip. Then in the bottom left, we have also restraints on the C deltas. So now the first 3 rings, atoms in the ring are glued together, and you see that no flipping occurs anymore. And in the bottom right, we also have restraints on the C epsilon, so the rings glue even more together. And now I've listed the results of this in this table, where you can see that these restraints drastically improve the sampling. So I've listed the absolute error between the predicted delta G and the experimental delta G here. And you can see that upon applying restraints further than C gamma, both the absolute error and the expected error, the standard error of the mean between replicates, drops down a lot. However, we do see that it slightly starts increasing again, the error, after we start introducing more restraints, although this is not very statistically significant. But still, it led us to the assumption to believe that we can also over-restrain our mutant conformation and limit its sampling freedom. So now I want to come back to this Barnay's results slide to show you that we try to do there we are, to show that we did some manual intervention. So instead of the automatically generated mutant conformation, we tried to tweak it around a bit and let it start in what we thought would be maybe a better position. We tried different restraints, and from all these combinations, for each mutation, we picked the best result, which is of course cherry picking. But it's I wanted to show that there we are, laser, that the MAE drops down a lot. The performance is now really well. The only problem here is, of course, that we know the delta G that we are looking for. And in a case where you do not know which delta G you're looking for, you cannot apply this. But at least it shows us what the protocol is capable, or the method is capable of. And we would like to learn from this as much as possible to put as much of these choices into the generalized protocol. Here I wanted to list some, as I would say, hyperparameters for the protocol that we use now. So we use a 2-FEP stage protocol, which would be applicable for any kind of mutation. So prior to this tryptophan, where we would have 9 FEP stages, and then if your mutant is different than the alanine, you would need even more FEP stages. You can now always do it with just 2, where in the first FEP stage we turn off the charges on the wild type and introduce softcore, and also on the dummy mutant atoms. And in the second FEP stage, it's mirrored, and now the wild type is completely turned off into dummies, and the mutant is completely turned on. Right now, very quick way to generate the mutant conformations is with the pipe mutagenesis, but we have also used it with AlphaFold predicted mutant conformations, which does not improve the results as much as we hoped. And for restraints, we are now using restraints between equivalent heavy atoms. So when the mutant conformation is predicted to overlap with the wild type, we would use, in this case, only the restraints on these C beta and gamma, and not on the oxygen, because it is a different atom type than the carbon in the wild type. We've tested and benchmarked our protocol with the OPLS AA force field, but we can also use it with Amber and Charm, and we use the TIP3P water model. And these are some settings for the sphere radius and time step and the lambda propagation that we use. And I wanted to show the computing performance, so running the full set, if you have available distributed computing, for us with maximum 16 processors, we could run the whole set in less than 2 hours, so, which we're quite happy with. So now for the future prospects that I wanted to show is we would like to try to determine problematic mutations a priori. So still, even with the cherry-picked results, we still see some large outliers. And we would like to understand why these particular mutations are still outliers. So we'd like to define some descriptors with intrinsic chemical and dynamical information of the specific residue mutating, but also the full protein. And hopefully with these descriptors we can capture certain culprits that lead to the problems for these mutations. So we want to train a neural network there and find a possible relationship, and hopefully predict the expected absolute error of the delta G rather than the delta G itself. Now this is a very quick model that I made on just a Barnay set, so it's way too few data to do any machine learning, but it showed some promise that there is something available there with R squared after averaged over multiple times training this model. So we're optimistic that if we use our protocol for many more data sets, we can start training something that is gonna give us a bit more information there. So in summary, QresFEP2 is accurate, fast, and reliable, and we have comparable results to alternatives in a short amount of time. Distance restraints are very important, and they prevent flapping, but they could also over-restrain. And of course, the mutant conformation that you choose therefore is very important. We still encounter a few large outliers, and we expect these are due to certain culprits, which we hope to capture by training a neural network. But for this, we need more data collection. Then to the acknowledgements, I would like to thank the founding father of QresFEP, which is Willem Jespers. Then my supervisors, Hugo Gutierrez Terán and Johan Okvist. Master students have worked on this project, and the rest of my lab. And you all for your attention. Thank you.
We have some time for questions, yeah.
So very nice presentation, thank you. Now, given the issue that you worry about the restraints doing the right thing, I think the obvious thing to try would be to look at, say, leucine to alanine and isoleucine to alanine and take the difference there. That's your gold standard.
Okay.
And then if you play with your restraints, you have to be able to reproduce this gold standard. It's what we do with relative versus absolute solvation-free energies. You do 2 absolute, and the relative has to match exactly, otherwise something's wrong.
Okay, that's a very good point. We'll definitely look into that. Thanks. There in the back.
Thanks for the very nice systematic work. Appreciate that you still have to publish it, but could you allude a little bit on a surprising culprit of a mutation?
Well, actually, now that you mention,
you didn't expect.
That you mention it, due to the time, I didn't want to include this, but I have a slide for it. So, of course, the force field. What we see with this more hybrid topology approach is that you're touching bonded parameters, and that's something that could lead to errors, which we also saw for this tyrosine to phenylalanine one. Of course, wrong mutant conformation. For this, you would maybe need to run much longer simulations, but then we take away a bit of our quick performance that we have now. So we would like to think that with AlphaFold we would have a state-of-the-art prediction tool, but still then we see that not always we perform as we hope. Of course, insufficient sampling, so because we use a sphere, sometimes, as you can see here now in the top, a part of the system would be cut off, so we cannot have full global rearrangements that we would capture, but we would not expect to capture that anyway in the time frame that we simulate. And one thing that's particularly important that we want to look into soon is missing buried water molecule, that if large gap gets created from going from a larger to a smaller residue, then you need to account that this water also, if there should be a water, then you have to capture it in your simulation as well.
And maybe one final question. Do we have any?
What is your unfolded representation of the
So
system?
we use now a tripeptide, so that will be the residue, the mutation you're looking for in the middle, flanked with 2 alanine residues. But in the previous work, it has also been investigated with a pentapeptide, so there will be like 2 alanines on both sides, or also with the actual wild type residues flanking, so both tri or pentapeptide. But it all shows that the results are very similar. So this alanine tripeptide approach is very quick to implement and easy, and it yields very nice results. So, yeah.
Let's thank Lucien again.
Thanks.